Fine. I'd like to talk to you this morning briefly about the FINESC project and what we're doing for energy applications using ICT. So the FINESC project is addressing the energy sector, smart grids or smart energy, as we call it. We try to avoid discussions about definitions of what a smart grid is, so we talk about smart energy. The context we're working in is that in the upper part of the diagram you see energy networks as they are today. Generally, the networks were designed so that the energy is generated in a power station and is sent in one direction to the consumers, whether that's industrial or private consumers. And the network was designed, the energy network, as a one-directional flow. There was very little need for monitoring or control in the network because you knew what you were producing, you could see what the load was, and you could keep the network balanced by varying what you produced. But today, with so much deployment of solar and wind and biomass, you have a very different network in reality. The network is being used in a different way, but the architecture hasn't changed. So the architecture and system design was for a one-directional network without measurement or control and using power generation as the balancing mechanism. But today, you have lots of solar power and wind farms pushing energy into the power network and running it backwards effectively as a bidirectional network. And that's creating big problems because the energy providers can no longer just balance the network by, or can't always balance the network just with the changing the load from their power stations or the generation at the power stations. And increasingly, they need to know how much energy is being put into the network by the renewable energy sources. And when they don't manage to measure quickly enough, and there's a low load on the network, such as happened last year in southern Germany twice in June at weekends. You can have a network blackout because the circuit breakers are triggered because there's too much energy going into the network from solar powers. On a sunny weekend, a sunny Saturday afternoon, very little industrial load on the network and a lot of energy coming in from all the solar panels in southern Germany. And that was what happened in Germany last year. On one occasion, it was just caused a blackout for about 4 hours in the whole of Munich. And another occasion, also a weekend, there was a fire in a transformer substation because the circuits hadn't triggered quickly enough and the transformer went on fire. So you can see already that the problems are there and it can be very difficult for energy providers to manage this situation. And what's needed as a first step is more monitoring and measurement equipment deployed in the energy distribution network, and that needs communication. So the network wasn't designed in that way. That type of monitoring and control and communication wasn't needed when the energy networks were built, but now it's needed because of the energy coming into the network from all sources. So this is one of the big challenges that energy providers face, and they need communications. At the same time, the new sector actors who are operating wind farms and solar farms, they also need communications because they need to know who's producing what, how can they amalgamate their production so that they look like single large producers from many smaller wind farms or solar farms, and they want to sell their energy on the bigger energy markets, and they need extensive ICT facilities and very fast reaction times to be able to do this. In the consumer side, people want to save energy, they want to use it in a more sustainable way. And the sustainable way to use energy, particularly power, is to use it when it's being generated locally. So if your solar panels are producing electricity, you should use the electricity as it's produced. And one of the ideas with electric vehicles is that people should charge their own electric vehicle with the power they themselves produce from their solar panels. If the car can be charged during the day, for example, then you have the issues that the sun isn't shining at night when people generally want to charge their car. So then you get into the complications of battery storage and how to manage the energy in the house or in the region. And the way energy providers see the smart grid evolving is that the grid will be balanced locally. so that the energy production is equal to the energy used on a local basis for industrial estates, for regions, and if not for the region, then for the country, and if it can't be balanced at a country level, then internationally. So they want to work from the bottom up to build the smart grid from small units rather than having it's a distributed system, rather than having a single, more or less centralized system as it was currently designed. So this is the area where FINESC is working, and we're focusing in particular on the overlap of ICT and energy, which we call smart energy, and within that area on internet technologies. So we're not necessarily talking about the use of public internet, but internet technologies and interfaces can be used in private networks, and they bring big advantages of scale for energy providers. And they provide an opportunity for energy providers to have access to all the innovation which is happening on the internet. Because these days, pretty much all innovation is driven by IT-based systems with IP interfaces. And if you're not using standardized IP interfaces, you can't use any of the new advances. You have to have it reprogrammed to the interface you're using. And in many cases in the energy sector, people are using privately developed networks that they've developed over the years. And many, even small energy providers might be running up to 15 different network types, running from very old ones installed 30 years ago, built to their specifications, to some IP and perhaps even public internet-based systems. So they have a huge range of networks to manage, even as a small energy provider, and still can't take much benefit of modern innovation, because they don't have a consistent system with IP interfaces. So there are big advantages to energy providers. Also in using standard components, they can build trials much more quickly. And that's something we've demonstrated in FINESC already. And in FINESC, we're building trials in 7 countries. The pink dots are where the trials are. The black dots are where the partner companies in the project are. If I start talking about Malmö in Sweden, there we have a smart city trial where E.ON is rebuilding a city centre harbour area with a smart grid approach. So with renewable energy sources, solar and wind power, operating a virtual power plant, so combining all these sources to look like one big power plant instead of many small solar and wind power situation. And then balancing the network so that you have energy monitoring and storage in apartments and in office blocks. So within a small area, balancing the whole energy management. And that's a smart city example. And then in Denmark, we have the counterpart, which is a smart region. And there we've equipped 20 houses with heat pumps, energy monitoring equipment and energy management equipment, and electric vehicles. And the idea is that in regions of Denmark which aren't connected to district heating systems, that the energy usage needs to be optimized. And again, the issue is to balance the energy usage locally. And we want to see what efficiencies can be achieved in a rural setting, so with a village setting. And we've chosen, we had a competition last year to choose the right village, and 3 villages applied. We chose the winner before Christmas, and the trial is already up and running, and we have first responses from customers and first videos. We've made a first video with the live customers on the trial, which you can see outside on our stand. In between Germany and Belgium, you see 2 pink dots, and there we're running more or less between Cologne and the North Sea, a virtual power plant. We're combining energy sources to look like one big power plant, and we're combining solar, wind and biomass in Belgium and Germany, so cross-border, which has regulatory challenges and legal challenges to be able to do it, apart from the technical challenges that there are different standards for the power networks in the different countries, and you have to overcome that as well. But this is now close to up and running, and we have one load on the network, which is a new factory built in Aachen to produce electric vehicles. It's a state-of-the-art factory, and in this factory we're looking at the production schedule to see if we can shift the production so that the energy-intensive parts of production are done when solar energy or wind energy is available. And we're looking at the whole production schedule to see if that's possible and if it makes sense in terms of improving the use of energy in the factory. And that factory is connected to the virtual power plant. By the way, if you'd like to see the factory, we have an open day on 12th of June in Aachen, where anybody can visit and see the newly started production runs of electric vehicles. And Deutsche Post has put in the main order for the first couple of 100 vehicles, and they already have delivery of the first electric cars and small vans for delivering post. Then you see in the south in Italy, in Terni, which is about an hour's train ride from Rome. It says City Utility ASM Terni. They're running an electronic marketplace trial with their 15 largest customers to see if they can optimize the local usage of energy by their big customers. They want their big customers to use the energy when it's available and to try to, again, reduce transmission losses in the energy and better optimize the use of energy in the network. In Spain, Acciona is running a smart building trial, which is linked to the trial in Horsens. And we had a demonstration open day there last month, which was very well attended. And in Ireland, we have two trials. One is looking at this issue, which I've mentioned, of the energy distribution network, where you need to put in monitoring and control equipment. And there we want to link electricity substations with communications using standard IEEE 61850 communication messages, which are the standard for the energy sector communication, and transmitting them over LTE and other communication facilities, looking at the delay and what's possible and seeing how the whole thing works. And the second trial, which is by far the bigger trial, is looking at the potential to balance the network, particularly in countries with a lot of wind energy like Ireland, using the ability to turn on and off the charging of electric vehicles. And the concept there is that when the wind power is generating about 50% of Ireland's electricity most of the time these days, it can even reach 70% at some days. And the problem is that the wind doesn't blow constantly, so the energy production isn't constant, it varies. And when it reduces, you either have to switch on a power station, a gas-fired power station, or reduce the load on the network to keep the voltage and the frequency stable. At the moment, what's done is to turn on the gas-powered electricity generating station in Dublin to balance the network if the wind dies down. But the plan, the trial we're running in Ireland is to see if you can switch off the charging of cars for a period of 20 minutes or 30 minutes. Typically, it would be during the night. And then switch it back on again, still have the car always charged to the minimum agreed level, 50% or whatever it is with the customer, and that it's fully charged in the morning, and balance the network without turning on the gas-powered electricity generating station. And that has a very good business case because it's very expensive to keep power generating stations running in standby. It's called spinning reserves because the turbines are spinning. They're ready to be switched in milliseconds, and you've got a full staff, a full power generating station using gas, even though it's not producing electricity, and it's a very expensive operation. And you could install an awful lot of smart chargers in homes with electric vehicles and communications for the cost of maintaining electricity generating stations in standby mode. And that's the business case we're looking at in this trial. We're using a fibre optic network with a distributed optical switch and LTE communications to the smart chargers, and we want to see how fast can we switch off the charging to the cars in reality, given the distances of up to 200 kilometres that we're dealing with in some cases between control centres and homes and the network locations. And if we can do that within what's called primary response times, it will be very valuable to the energy providers. It's fairly sure we can do it in secondary response times in something like 10 milliseconds. But if we can get down towards 3 milliseconds, it's much more valuable to the energy sector. And this trial is looking at the performance issues and how it works in reality. Where we should go live in that trial September this year. Virtual power plant is going live in Q2. The trial in Denmark has been live already since beginning of February, and in Malmo it's just going live now, and we'll have a demonstration in a couple of weeks' time of the first version of the trial. So that's roughly what we're doing in the trial sites. This is the architecture we're using in the project. We have more or less separated trials in different geographical locations, but they're linked by an API layer. So all are producing an interface to the trial infrastructure via an API, which has a lot of commonality across the trial sites. So if you're working with the API for the smart home and prosumers and using, for example, weather data or solar production data, you can use exactly the same functions and calls to retrieve the same information in the trials of smart cities. We have had, we ran an open call. We have 12 new partners joining the project on the 1st of May this year. As a result of the open call, almost all SMEs and some research institutes. We have a contest ongoing for students where we have a hackathon, and the winners will be working with Ericsson as interns to further develop the ideas on the APIs. And we plan to extend our project to September next year within our existing budget, and we will support phase 3 SMEs that want to work with the trials. So until probably April or May next year. So the first round from the first call of phase 3 projects. The Incense project is the main project in phase 3, funding smart, what do they call it, green tech, smart energy SMEs. We're working very closely with them, and they're presenting in our open days. And there are 4 phase 3 projects dealing with smart cities and smart energy, and we have contacts with all of those as well. They're not specialists in smart energy, but if they have SMEs that want to use the infrastructure, we'll be discussing with them as well. So I mentioned that if you'd like to see the electric car factory, which is a leading state-of-the-art production facility in Europe, you're welcome to come to Aachen on June 12th. In September, probably 3rd week of September, we have to fix the date or finalise the date. We'll have demonstrations of the trials in Ireland. On the electric vehicle charging. In December, we have a demonstration of the smart region in Horsens, Denmark, and in February, the electric marketplace, and June in Malmö in Sweden. But we can organise links for SMEs to these trials at any stage, but these are the planned open days where we'll have press coverage and fairly big events. The student contest is open, and anybody is welcome to join our innovation community to follow what we're doing. We send occasional mails, inform you when the events are coming up, and you just enter your email address on the website or give us a business card. We'll add you to the list. So that's a short overview of what we're doing for SMEs in the smart energy sector, and we're very happy for contacts and ways to help other groups and achieve synergies from our project.
Thanks, Fiona, for presentation. Maybe we can take one very quick question.
Everything clear.
No questions? Thank you for your presentation again.